Hello and welcome, my name is Matt and you are watching Casual Physics. This video series is about guesstimation, which is all about how do you solve impossible problems. Why would you want to do that? What's this really all about? Please head back over to video number 1 for the answer to that question, because this is video number 5. We've been here a while now solving all kinds of problems like how many atoms are there on planet Earth, how many pickles were eaten in London last year? Very important problems, I'm sure you will agree. And we've been kind of building up some essential skills along the way, skills of guesstimation. And so if this is your first guesstimation video and a few things just don't make sense, please consider going back to those earlier videos as well. Today we are continuing the food theme from last time, but now we're going to get very practical with the question, can you grow your own food? Now, I don't know about you, but I often have this fantasy of being self-sufficient, having a bit of land and growing all the food that I need. And I even had a go at doing this last year. I grew some courgettes, which was great fun until the mildew got them. And this is the point, right? It's fun, but there's a difference between fun and survival. The simpler life is, of course, very romantic, but probably not as fun as we really imagine it to be. And so for me as a physicist, I kind of think, well, what are the physical limitations of growing my own food? Can I use some basic physics knowledge and the tools of guesstimation, of course, to figure out how much land would I actually need to pull it off? Is it a garden or is it more like a farm? Let's find out. As always, we begin with what do we know? Do you have any numbers in your mental wiki that can help us solve this problem? So take a moment, pause the video and think, do I know anything about food, about growing plants, about our needs as humans? Take a moment. For me, when I think about food, I think about calories, which is energy. And so we're going to start thinking about things from this point of view. And in general, kind of side note, whenever you have a problem like can I do X or is X possible, thinking about things from the point of view of energy is really helpful. And the reason why is because energy is just what makes stuff happen, right? It makes things go, it makes things glow, it makes things grow. Energy is a kind of universal currency. And crucially, you cannot fool the energy accountant. If you don't have enough energy, things just won't happen. And so thinking about things from an energy budget perspective often helps to simplify a very complex looking situation, which we do have, right? We've got lots of things we could consider, like the type of crop, the rainfall, do we have any pests? We don't really want to get bogged down into those details because this is guesstimation. Energy is going to be really helpful for us to simplify things. So, energy, what do we know? Well, we know that we get our energy from plants. We know that plants get their energy from the sun. There is a limit on how much energy comes from the sun, so there is a limit on how much food we can grow. Sounds reasonable. Can we quantify this? Well, let's begin with thinking about our needs as humans. How much energy do we need to survive? Again, pause the video, take a moment. Can you use your knowledge of life to figure out any numbers that relate to energy and human food consumption? The number that got drilled into my head at school, and you can find it on the back of some food packages, is 2,500 calories per day. This is the daily energy requirement for an adult male. Now, a food calorie is kind of a weird unit of energy, and that's because one food calorie is the same as 1,000 physics calories, which is annoying to say the least. And in general, units are kind of annoying and kind of boring, but they are very important to get right, and so we do need to get on the same page when it comes to our units. So we will of course be using standard international or SI units to do our calculation. The SI unit for energy is the joule, named after this guy, looking very intense here. This is James Prescott Joule, who was a mathematician, a physicist, and also a great brewer. One food calorie is about 4,200 joules. We want 2,500 food calories, that's just 4,200 multiplied by our 2,500. And now we can do away with those pesky food calories and flex our scientific notation muscles. We learned from video number 3 that we can write 4,200 as 4.2 times 10 to the power of 3, which is 4.2 multiplied by 10 3 times. Similarly for the 2500. This is guesstimation, so it's okay to turn that 4.2 into a 4 because it makes the maths a bit easier and we end up with a nice 10 up front. You may recall that when it comes to multiplying powers, we can just add them up. And so we end up with 10 times 10 to the power of 6 joules. In words, what is 10 to the power of 6? It's 10 multiplied by itself 6 times, which is 1 million. And so what we've got here is 10 million joules for the daily energy requirement for a human, which is a really nice round number. Thank you very much, Mr. Joule. It is worth saying that sometimes we get bored with writing 10 to the power of 6 because, well, apparently it's just not short enough for us. And so sometimes you will see people writing this 10 mj, which we say 10 megajoules. Okay, this 10 megajoules of energy that we need every day, that's got to come from the plants. The plants get it from the sun, and so the next question is, of course, how much energy actually comes from the sun? Take a moment, pause the video, have a think. What numbers do you know in your mental wiki that can help you with this? If you've had some solar panels installed recently, you may have a good sense of how much energy gets delivered on a good day by these panels, and that can help to give you a good sense of how much energy is available for the plant to grow. I don't happen to have any solar panels, and so I'm going to have to use some other numbers in my mental wiki and the geometric mean, which I promised you last time we would get more opportunity to use, and so here we are. I happen to know that the solar power reaching the Earth's surface is at most 1000 watts for every square meter. Now, what does that mean? What is this thing that I've just introduced called power? Power is a measure of how much energy is flowing or being used in a given time, and it's measured in the standard international unit of watts after this guy, Scottish inventor James Watt. 1 watt is the same as 1 joule per second. So if I use 1 joule of energy in 1 second, then we say I am using energy at a rate of 1 watt. Now let's try and get a feeling for this new unit. A few minutes ago, we were actually calculating the power that a human consumes just by being alive. We calculated 10 megajoules of energy per day. That's energy in a given time. That's power. So now let's express this in the units of watts so we can compare it with the power from the sun. So we have 10 megajoules per day. That's 10 megajoules divided by a day. 10 megajoules is 10 to the power of 7. And how long is a day in seconds? 86,400. That comes from 24 hours of 60 minutes of 60 seconds. Okay, let's now be cavalier, this is guesstimation after all, and approximate that 86,400 as 100,000, which of course in scientific notation is 10 to the power of 5. Why do we do this? Because calculating with powers is easier. When dividing by powers, we subtract them. So we have here 7 minus 5, which is of course 2, otherwise known as 100 joules per second or 100 watts. And so every human is actually using 100 watts of power continuously. And for those of you who remember the days of incandescent light bulbs, you will recognize this as a kind of a bright light bulb that kind of fills a room. This is what humans need continuously. And now we can do a simple comparison between the sun and us because we've got the units the same. And what we can see here is that the sun gives us 10 times more power for every square meter than we need to stay alive, which is amazing. And superficially, this sounds like we hardly need any space to kind of provide our energy needs to grow our own food. But this solar power is the very maximum that we can get. And we've got to consider, among other things, all the inefficiencies in the plants, right? The intermediary between the sun and us. And this is what we need to do next. Come up with an effective power, a kind of average power from the sun through the plant and into us that takes into account all the inefficiencies of the plant and any other practical realities along the way. It's only then that we will be able to do a proper comparison between what the sun provides and what our needs actually are. Firstly, we've got to consider night and day. That effectively reduces the power by half because the sun doesn't shine half the time. So we're immediately down to 500 watts. Then we've got to consider the profile of the sun. It doesn't provide constant power throughout the day. The power goes up, peaks around midday and goes to zero at dusk. And so on average, we're getting only about half of that power. So we're down from 500 to 250. Then we've got to consider clouds. Now this one is more complicated, depends on where you live, but I can tell you here in the UK, we have clouds about half the time. So that reduces the power again by half. We're now down to 125. So we've already lost a factor of 10 from our solar power, and we've not yet even talked about the plants. How much energy do they actually absorb, for example? Now, I don't know much about plants, honestly, so I'm going to use the geometric mean to figure this out. The maximum they can absorb is, of course, 100% of the solar power, and it seems unreasonable to think they would absorb less than 1%, and so we've got square root of 100 times 1, which is 10. And so that takes us down by a factor of 10 to 12.5 watts. And because this is guesstimation, let's make the maths easier, make that into a 10. Now, how do the plants use this energy? Well, plants use the energy to grow and also maintain what's already there, just like we do with our own bodies. I've got no reason to believe that growth is more important than maintenance, so we'll say 50% for growth. So that knocks another half off our power. We're now down to 5 watts. Okay, how much of the plant do we eat? Well, this depends. Certainly less than 100%, more than 1%, otherwise it probably wouldn't be worth us growing it. So the geometric mean gives us, again, a nice 10%. So we're losing another factor of 10, we're down to 0.5 watts. Finally, crops don't grow all year round, do they? About half the time crops are growing, so that knocks off another half to give us 0.25 watts per square meter for the effective power that comes from the sun through the plants and into us. Okay, we started with this whopping 1000 watts per square meter as the power coming from the sun. And we thought, well, this is all available for us. But no. Only 0.25 of those watts are practically available to kind of grow food and provide our energy needs. And that's a big difference. It's a 4,000-fold reduction in power. And so that huge difference really underscores the power of guesstimation. We were able to incorporate a lot of real-world stuff in our calculation just then. And how were we able to do that? We didn't get bogged down in the detail. And so we were not kind of afraid, we were not overwhelmed by all the real-world complexity. We were able to do something rather than getting kind of stuck. And this is the danger of real-world complexity. It's hard, and so often you just want to ignore it and hope that it goes away. But as we see in this example, the real world stuff can be really important, and so you need a tool to be able to deal with that, and that is, of course, the tool of guesstimation. So now we're going to go back to our problem. Can you grow your own food? Perhaps better phrased, how much land do you need to grow your own food? And this is now just a simple calculation. It's how much power does a human need? Divide this by the power per square meter coming from the sun, through the plant and into us. And this will give us a number with units of area. And finally, we have 100 divided by 0.25, and that gives us 400 square meters. And so if you've got a 20 meter by 20 meter plot of land, then yes, you can grow your own food and live the simpler life. It's not like buying a gigantic farm. It is more like a garden, which I think is pretty cool. Final question. How close did we get? What is like the right answer here? Of course, there's no single answer, but of course we want to know how close did we get to an authoritative estimate on this question. And so of course, what did I do? I went over to good old Google and typed in how much land do you need to grow your own food? Pretty simple, and I want to show you what the results were because I was very excited by them. So here we go, we're over at Google. How much land do you need to grow your own food? And here we have the answer. In fact, I don't even need to click on it. Research in the 1970s showed that you need 370 square meters. So we are less than 10% off a kind of an authoritative research-based answer, which I think is amazing and of course underscores once again the powers of guesstimation. And so that brings us to the end of our time together today. I hope you've enjoyed it. It's either been just pure fun, doing some guesstimation, or maybe it really did stimulate you to think about a possible future simpler life. Who knows? But I hope you enjoyed it. Next video is going to be rubbish, like quite literally rubbish, trash. That's the theme of the next video. So you can look forward to that. And yeah, just once again, thank you for your time and attention. I really appreciate you being here, and I look forward to seeing you very soon. Bye for now.